So welcome back. In this video, we are going to talk about our perception of multiple frequencies at once. So the idea is we're going to have two different sources of sound. We'll focus on the case where those sounds have the same amplitude, and we're going to alter the frequencies relative to one another. So two pure tones with frequency F1 and F2, and I want to investigate how we perceive the different combinations of frequencies. And so we're going to just start with a demonstration. I will start with the frequencies being equal and then increase one of them. And so just pay attention to what this sounds like. Maybe take some notes on what you hear, and then we're going to talk about the various effects that we perceive there. So I'm going to play two tones. One of them is going to stay at 400 hertz, and the other one I'm going to gradually increase from 400 hertz. 401. Okay, so that was it. We'll go back and listen to parts of that again after we discuss. So in order to understand what we just heard, I want to go back and think about the displacement graphs for the sound waves for these two frequencies. And a good starting point is actually the simple case where you have exactly the same frequency. So frequency 1 equals frequency 2. And so in this case, you would think that, okay, you just play the two frequencies and it'll just be the same sound but louder. The interesting thing is that depending on exactly how those are timed relative to one another, you could actually get the combination of the two sounds being louder, or in some cases, they could even be softer than before. And so let me do an example where, so we've drawn the two frequencies and they're perfectly lined up. The ups and downs of the two sinusoidal waves are what we call in phase with each other. And so there we know that the combined sound, according to our principle of superposition, we can understand the combined sound wave as just the sum of the sound waves 1 and 2. And so that would be a sinusoidal shape with a larger amplitude than before. But the other thing you notice is that you could get a different result if graph number 2 is shifted in time relative to graph number 1. And so if it's shifted in time by a half of a period, well, then the first sound wave is going to go up when the second one goes down. And that means that the air molecules from the first sound wave would be displaced one way, but then the second sound wave is trying to displace those air molecules in the other way. And so what happens is that the sound almost cancels in that case. And so the physics jargon that we use for these two cases that you can have is that in one case you get constructive interference, the sounds add up to a bigger sound. In the other case, you have destructive interference, where the sounds actually, even though you have two different sounds playing with the same frequency and the same amplitude, the combination of them gives you something with a smaller amplitude. And that could be, in a perfect situation, that could even be going down to 0. And so that's actually the physics behind the noise canceling headphones that you might have experienced. So these noise canceling headphones, they're basically just figuring out what are the sounds coming in from the outside, and then they produce some sounds. So they kind of split that into frequencies, and then for each pure tone, you could imagine these headphones are producing a pure tone with the same amplitude, but shifted in by about half of a period, so to get this destructive interference. And so if that's done right, it can very effectively cancel the noise coming in from the outside. So it's almost magic, but it's just a basic consequence of our superposition principle. Okay, so a great way to demonstrate these constructive and destructive interference phenomena is the situation where you actually make the two frequencies slightly different. And so this is the thing we heard at the very beginning of the video when I increased from 400 hertz on the second sound to 401, then 402. And I'm going to play that one again for you in a minute. But let's just understand theoretically what was going on there. So what you heard was that single tone that we started with, it appeared to get louder and softer and louder and softer in a regular way. So we can understand this using this constructive and destructive interference phenomenon. Okay, so let's imagine that we have those two sound waves pretty much oscillating together, so adding up and constructively interfering. But because one of them has a slightly different frequency than the other, what's going to happen is after a little while, they're now going to be out of phase with each other. And so when that happens, then the two sound waves are going to add up destructively, and so the sound is actually going to partly cancel. So you can actually see that here. I've plotted the two sound waves, and at the bottom, I've just taken the mathematical sum of these two sound waves. So they almost look the same, but they're not quite the same frequency. And you can see these lines, the vertical lines show that at this point, the two waves are pretty much in phase with each other. One goes up and the other goes up. But by this time over here, they're out of phase. This one goes up and that one goes down. And so the result is that you get an oscillation, but the total amplitude is big here and small there, and that just repeats periodically. So they're in phase, they go out of phase a little bit, they come back in phase, and they go out of phase again. And that is a periodic phenomenon with a frequency that turns out to be exactly the difference between the original frequencies that we're using. So if you had a bigger frequency difference, then that getting louder and getting softer, the period of that becomes smaller and smaller. The frequency of that becomes larger and larger. So this phenomenon is what we call the phenomena of beats when we're talking about the sounds of two closely separated frequencies. And this is something that musicians use all the time in order to tune their instruments. And so if you have two instruments that are slightly out of tune, then you'll hear those beats, and you can adjust the tuning until you don't hear the beats anymore. So let's actually go back to the video from before, and we'll just hear those beats one more time. So I'll just start that up at this place. 401. Okay, so you can clearly hear as I increased the frequency of the second sound, then the frequency of the beats got faster and faster. Okay. And you notice that we didn't yet hear two different tones. It was really just one tone with this getting louder, getting softer. So there has to be a much larger frequency difference for us to actually perceive the two different notes as being different. And so we can then talk about, well, what did we hear as that frequency difference increased? So at some point, the beats got faster and faster. And when the beats were very fast, I think we started to perceive them as more just like a growly character to the note. And so there was, for a little while, I think pretty much still just one note that we could hear, but it had this roughness to it, almost like a car engine. And so that's what we perceive for a little while. As we go beyond this regime where we can clearly hear the beats getting louder and softer, it's just like our tone, which is rough in character. And we would say that the frequency of that combined tone that we're perceiving, it's like the average frequency of those two different sounds. Now, at a certain point, we can start to hear the two different frequencies more distinctly. Okay, so instead of hearing one note with some roughness to it, we hear definitely two notes. We hear the original 400 hertz, and we hear a higher frequency tone. And so the place where we start to hear those two separately is called the frequency discrimination limit. Okay, so that's just a particular difference in frequency where above that you hear two tones instead of just one tone. Okay, so that would be the next case as we increase, that we would get above the frequency discrimination frequency and we'll hear the two tones, but then we still hear this roughness that kind of originally was related to the beats. Now, one thing that you can begin to hear a little bit later, as the difference in frequencies becomes even higher, when that becomes like 60 hertz or 80 hertz, so then you actually start to perceive the beat frequency as some kind of a musical tone as well. So let's actually look out for all of those things. So I'm going to play the next range of frequencies again. So we should hear originally like a single tone with this roughness, then two tones again with some roughness, and we might start to perceive a third tone as we get higher, and I'll kind of point that out when we get to it. So let's start from here. So just to jump in, at this point, I could pretty clearly hear a low tone. Let's just hear it again. Can't quite sing that low. Let's try. Okay, yeah, I didn't sing the right note, but it was something down there, and so we could hear. I'll just go back a little bit, hear it one more time. So we should be able to hear sort of the original 400 hertz, which I'll play one more time. So listen for that tone, and a higher tone and a lower tone when we get up there. Okay, so let's listen for that. Okay, so I'll have the link to this so you can play around with that on your own. And all of these things are somewhat subjective, and so it's going to be experienced in a different way depending on who you are and how your brain works. So the things that I'm saying might not exactly be true for you, or they might happen at different places for different people. But I think more or less these are the agreed upon phenomenon. Okay. And so finally, once we got to a large difference in frequencies, then we hear two fairly clear pure tones. So once we get like to the end of the video, Let's hear that one more time. So jumping all the way to the end, then we can hear, it just sounds like two different notes. Okay. So we also have some terminology for that place where this roughness kind of disappears. Sorry, I'm jumping around all over the place. Where this roughness disappears, that's what's known as the critical band frequency. So if we're above this difference where now the roughness disappears and we hear two distinct, clear, pure tones, and that's it, then we say we're above the critical band. Okay, so that was some jargon, but let me just summarize all of that right here. So we have the graph shows the difference in frequencies, and so as we go up from 0, we first heard the beats. We understood those to be a consequence of the constructive or destructive interference when the two waves were in sync or out of sync. When the beats got too fast, so maybe above with a frequency difference of 20 or higher, then it was like a single tone that we perceive, which is the average of the two frequencies, along with some roughness. Above what we call the frequency discrimination difference, then we could hear those separate tones F1 and F2 at the same time, along with the roughness that we had before. And this roughness, or like engine noise, that has a specific frequency eventually that we can perceive. Okay, so we could actually perceive the difference in those frequencies as some kind of a musical note. And then finally, above a certain place, which we call the critical band, then we really just perceive two pure tones, or two clear pure tones, and then F2 could be as high as we want, and we still just hear those two tones. So now we can turn to the question of why we experience things in this way. So, why do we have a hard time hearing the two separate tones up until this frequency discrimination limit, and why is there this roughness up until the critical band frequency limit? And it actually has to do with the fact that these two sounds are competing with each other on one ear. So the two sounds are kind of trying to both excite our basilar membrane inside our cochlea at the same time. Then they kind of compete with each other, and that gives rise to all these effects. So a very interesting point is that if I separately play one tone in one ear and the other tone in the other ear, you don't get these effects. Generally speaking, you basically just hear two frequencies, even if they're pretty close, and you don't hear the roughness that you hear when they're going both in your same ear. And so this is really indicating that it's because you're trying to hear those two sounds with the same piece of biological machinery, and they're messing with each other. So we can understand that better by recalling what's going on inside our ear, that we have this basilar membrane, that when you play the first frequency, it is causing that to vibrate in a certain region. So there's one place that corresponds to the frequency that we select, 400 hertz. So there'll be the particular place on the basilar membrane that is vibrating the most with that frequency. But then it also turns out that there are nearby regions that are also vibrating. And in terms of the signals going to our brain, there's nerve signals coming from the central region as well as these neighboring regions. Okay, so there's kind of a whole band on our basilar membrane that is excited. It's most excited in the middle. The largest, maybe most rapid nerve firings are coming from the middle there, and then less and less as you go outside of that. And so basically we could understand that if that second tone is trying to excite a region of the basilar membrane which is overlapping with that one, then that will cause this sensation of roughness or unpleasantness that we experience in between, in this below the critical band difference. This is what we're experiencing. And so this is actually a start on understanding the difference between like pairs of notes that are dissonant and pairs of notes that are perceived to be harmonious with each other. And we'll take this up a lot more in the next video. But for now, we could just say that what we seem to have understood by our demonstration is that if we hear two tones that are too close together, then there's some unpleasantness to it. There's some roughness to it. And we would describe those two tones as being dissonant together. Okay, so next time we'll start to talk about larger frequency differences, and we'll understand that there are some special frequency differences that are particularly harmonious, and we'll try to understand why that would be.